All right. The first test that we're going to talk about when we're talking about determining convergence of a series is the integral test. And so the integral test, first off, requires us to have a sequence of positive terms. And you will find that this is a very, very common need that we will have when we're trying to determine convergence of a series, that all of the terms have to be positive for these tests to work. And for series that aren't always positive, we're going to have a workaround for that, which we'll learn about today also. But this requires us to have all positive terms for a continuous decreasing function of x. Okay, so positive terms, continuous decreasing function of x is what we need for this particular test called the integral test to work. And so all it says is if that from some point on for all x values greater than or equal to some positive integer capital N, if that's true, then either both the series and the integral from n to infinity of the function that can be related to the series either both converge or they both diverge, which means that if we're looking for whether a series converges or diverges, we can rewrite it as an integral, as an improper integral from this n value that we're starting at to infinity of some function that represents each term of the series, and then evaluate that integral. If the integral converges, the series converges. If the integral diverges, then the series also diverges. What that does not tell us is the actual value of the series. It only tells us that it either converges or diverges based on what the integral itself does. Okay. Does that make sense so far?
Yes.
Okay, cool. So we will start off looking at this, the sum from n equals 1 to infinity of 1 over n root n. And we want to determine if this thing will converge. So what integral should we write to set this up? We should be looking at an integral from 1 to infinity of, and what function represents each term in here? If I rewrite it as x's, is there 1 over x root x, or that would be x to the negative 3/2 dx? Do y'all agree that that sort of makes sense there? Okay, so let's evaluate that integral. How do we evaluate that integral? We rewrite it as a limit, right? So we'll look for the limit as a approaches infinity of the integral from 1 to a of x to the negative 3/2 dx, which should then give us a limit as a approaches infinity of what's the integral of x to the negative 3/2. Should go up to x to the negative 1/2, and then divide by negative 1/2, which should make that negative 2 x to the negative 1/2 from 1 to a. Giving us a limit as a approaches infinity of what? Negative 2 over root a minus negative 2 over root 1. And what does that come out to be? Square root of infinity is still infinity. 2 over infinity is 0, so this becomes negative, negative, or positive 2. And so since this integral exists, since this integral converges to a value of 2, it tells us that this series also converges. So we would say that this converges by the integral test. And you'd want to make a note that it is possible for us to use the integral test because x to the negative 3/2 is always positive for, we'll say for x, I can write an x, for x greater than or equal to 1, and it's always decreasing. So because of the fact that it's always positive and decreasing, and the fact that the integral itself converges, that tells us by the integral test that this series also converges. It does not tell us that this series converges to a value of 2. It just tells us that it converges. That's all it tells us. And why does this work? Any ideas on why this works? Yes, Delphine, that's correct. The integral converges to a value of 2. The series does not necessarily. Because we have to think about what's the difference between, this is what I was trying to get at here. What's the difference between a series and an integral? Well, here's my positive decreasing function, right? Starting at some value along here, doesn't really matter where. If I am looking at the values of the, I'm looking at the values of this series, I'm potentially getting things that look like this, or I'm, depending on how I've labeled my series, looking at things that look like this, right? These values are, this x value, sorry, this is y value plus this y value plus this y value plus this y value. So if this series diverges, then, if the integral diverges, if the area underneath the curve from here to infinity is infinite and my values of my series extend out above it, then the integral itself, the series itself also diverges. But over here, if my integral converges, and these values are all below the value of that integral, then that means that the series itself also converges. Because remember, the series is just increments of one width with some height up here, right? This is my values of my series. And we'll call those, so y, we'll call those a sub n's, right? Times 1, and the next a sub n times 1 times the next a sub n times 1. So we're just adding together these little rectangles of width 1 and height of the value of each term of the series. And so that's the basic idea behind why it works. We're going to sketch it out. Hold on. Let me see what Adrian's writing here. Exception to that, where you could have definite area, but yeah, so that's not exactly the same thing that we're talking about here. So we're talking, Adrian, about area underneath the curve, solely area underneath the curve. And so either the terms of this series are extending above the area under the curve, or they are coming a little bit shallow below the area underneath that curve. And so when we find the value of the integral, which is the exact area under the curve, it's either finite or it's infinite. And so if it's finite or if it's infinite, that will tell us whether the value of the series is finite or infinite as well. But what you're thinking about is like it having, an infinite amount of area, but a finite amount of volume or something like that, which is what that horn did. But we're not talking about volume. We're not revolving around anything. We're just talking in 2 dimensions. Okay, so what we're going to try to do is we're going to try to use this integral test for any series in this form, 1 over n to the p, which is like the one we just did, right? We did 1 over n to the 3/2. So we're going to do 1 over n to the p. And these particular series are called p series. And they show up very, very, very often, and it's very, very important for us to know that if we have the series from 1 to infinity of 1 over n to the p, that it will converge only if p is greater than 1, and it will diverge if p is less than or equal to 1. It's very important for us to know this, and so we're going to prove that using the integral test. So let's start with p being greater than 1. So if p is greater than 1, what integral would we use to solve this? We'd look at an integral from 1 to infinity of just 1 over n to the p, or we'll say 1 over x to the p, dx. And if p is greater than 1, when we write this out as our limit, the limit is a approaches infinity of the integral from 1 to a of x to the negative p. What do we end up getting when we do that, when we integrate that? It's just a power rule integration, right? Instead of it being x to the negative p, needs to go up to x to the negative p plus 1. And we need to divide by p plus 1, right? Everybody agree with that? From 1 to a? Okay. So if we plug a in for our x value there, we get a to the negative p plus 1 over p plus 1 minus 1 to the negative p plus 1, which is just 1, right? Over p plus 1. And as a goes towards infinity, what is a to the negative p plus 1? Right? If p was greater than 1, that means that we were looking at something like negative 2 or negative 1.00001. What can you still tell me about this exponent up here? Negative p plus 1 is still going to be a negative value, right? And so what we might want to do is we could rewrite a to the negative p plus 1 as a to the negative p minus 1, drop it down to the denominator, and have 1 over a to the positive p minus 1 times p plus 1 minus 1 over p plus 1. And as a goes towards infinity, right, infinity to this power is going to become what? No matter how small of a root that is, it's still going to be increasing forever, isn't it? So this first term here is still going to go towards 0. And so we'll just end up with -1 over p plus 1, which is just some number, right? Because p was just some number. So this integral converged, which tells us that this series must converge if p is greater than 1. Good or no? Okay. What if p was less than or equal to 1? Let's say, what if p was less than 1? If p was less than 1, this would still just be a power rule problem, wouldn't it? So we'd still end up with the limit as a approached infinity of a to the negative p plus 1 over p plus 1 minus 1 over p plus 1. But now, since p was less than 1, so like a half, let's say, what does that tell you about this exponent up here? This exponent is now positive, which tells us that this whole thing is going towards infinity. And we'd have infinity minus 1 over p plus 1, which this limit doesn't exist. And so we're saying that this limit doesn't exist, tells us that this summation must diverge if p is less than 1. And then the last case would be, what if p is equal to 1? So if p equals 1, we're looking at the integral from 1 to infinity of 1 over x dx, which would be the limit as a approaches infinity of the integral from 1 to a of 1 over x dx. And what's the integral of 1 over x? That should be our limit as a approaches infinity of natural log absolute value x from 1 to a, which is natural log of infinity minus natural log of 1, which is infinity. And since that doesn't exist, we would then also say that for p equals 1, it also diverges. Does everybody see how we can use this integral test to prove this? Cool. So, very important to know and memorize these P series tests. And when you are on the AP test or on any of my assignments, if you use one of these to compare some other series to it, then you can just simply say that you use the P series test. You don't need to go and officially define these. Yes, this only works for series in this form, 1 over a variable to a power. Or I mean, you can liken it to 2 over a variable to a power, or any constant over a variable to a power. And the constant doesn't matter. The constant, like if I had a 7 up here, I can pull the 7 out into the front here. Everybody good there? Okay. So we are now going to start talking about this thing called the convergence theorem for power series, which this is kind of where we start to get into some of the rules. We've talked a little bit about this. As we were going through our power series, right, we knew that as long as that common ratio that we had was was 1, right, we knew that as long as the absolute value of x minus a was less than 1, then our series was going to converge if it was one of these geometric power series. So what our goal will be to do is to figure out what is that value of r for any of these functions that we might be looking at. And so this value of r is what I think I've called it before, is called the radius of convergence. So we've had a radius of convergence of like 5 for some functions or half for other functions, right? When we had something besides just an x within here. So if we can find that value, we know that the series will diverge for all values where the absolute value of x minus a is greater than r, but converge for all values where x minus a is less than r. And then what we're going to have to concern ourselves with a lot now will be the endpoints. So we're going to worry about the endpoints later this week. So that's one option for convergence, is that the series might converge on some limited interval. The second option is that the series might converge for all x, where our interval of convergence then we would say is infinity. That'd be a series like x to the n over n factorial. The series for e to the x converges for all x. Or the series might converge only at x equals a. And every series will converge at least at x equals a, because if you plug in x equals a, you end up with a series of 0 to the n, which is 0 times some constant. So you're just summing together a bunch of zeros and you'll get 0. And so if that's the case, the series converges only at a, diverges everywhere else, and we would say that the radius of convergence is 0. Okay. So capital R, our radius of convergence, and then we call the set of all the values for which it does converge the interval of convergence. Okay. So those are the 3 options for what a series might do. It might converge on a set interval, it might converge for all real x, or it might converge only at a and diverge everywhere else and have a radius of convergence of 0. So whenever you are trying to determine if a series converges or diverges, the first thing you'll do is look at it and say, okay, is it a p-series? If it's a p-series, then you say, okay, it either converges or it diverges, just based on what that value of p is. The second thing you will do, though, if it's not a p-series, is you will start to look at this test called the Nth Term Test for divergence. This is a test that will only tell you if a series diverges. It does not guarantee that a series will converge. So this test is only for divergence. So something we've talked about in the past is that for a series to converge, we know that the nth term has to eventually go to 0 as n approaches infinity, which means that the partial sums have to get closer and closer to each other, so that effectively the partial sum of the nth term minus the n minus 1th term just becomes 0. And so what we can say then would be that this, or any series, will diverge if the limit as n approaches infinity of the nth term, a sub n, either doesn't exist or is anything other than 0. So look at your nth term, look at the limit as n approaches infinity of it. If that limit is anything other than 0, you are guaranteed that the series diverges. Okay. But on the other hand, that does not tell you that if that limit is 0, that the series will converge. Because, for example, we just looked at one a second ago, right? We just looked at 1 over x, right? This series, the p series, 1 over n, the sum from n equals 1 to infinity of 1 over n. We just showed that this diverges, even though the limit as n approaches infinity of 1 over n is 0. Right? And something I probably should have mentioned back here is this series, which we know diverges. What is this series called? It's called the Might be something you've seen in physics. This is called the harmonic series. Okay. Sum from n equals 1 to infinity of 1 over n is called the harmonic series. The harmonic series diverges. Fun fact, the alternating harmonic series, though, negative 1 to the n plus 1 over n actually converges. We can talk about why that is in a little bit. But this harmonic series, if you look at the nth term test for divergence, you end up getting 0 as the limit as n approaches infinity, but the series itself still diverges. So when you start talking about this nth term test for divergence, don't use it ever to show that something converges. You can only use it to show that something diverges. Everybody good there? Okay, so I give you a series, you look at it, you say, all right, it is not a p-series, so I can't be guaranteed whether it converges or diverges just by looking at it. You look at it and you try to do the nth term test for divergence, and you find that the limit as n approaches infinity of the nth term is 0, so that's inconclusive. It tells you that maybe this series converges, maybe this series diverges. You move on to the next test, which we call the direct comparison test. And the direct comparison test is a test that only works, once again, just like the integral test, with series that have no negative terms, so series that are always either positive or equal to 0. And so what we will do with the direct comparison test is we will look at some other series that we know is similar to our series and try to compare them together. And so we'll look at perhaps a p-series that we might know that's very similar to the series we're looking at, or we might look at some power series that we know that's very similar to it. And in doing that, if we can find some point within our series such that at that n value, every other term in the series we're looking at is less than or equal to every term in the series we are comparing it to, and the series we're comparing it to converges, then that means that our series converges. Or likewise, if we can find some value where after that n value, our series is always greater than or equal to the series we're comparing it to, and the series we're comparing it to diverges, then our series will also diverge. So effectively, let's say we're looking at a nice simple series here. Let's just do the sum from n equals 1 to infinity of x to the n over n factorial at x equals 1. So what does that series look like? Started at 0, actually, just for fun. What does that series look like? Looks like 1, right? Plus 1 plus 1/2, right? Plus I plug in 3, that's 1 over 6. I plug in 4, that's 1 over 24, and so on. Okay. And what do we know about this series? Does it converge or does it diverge? Right, it converges. And the reason why this converges, right? We know this converges for all real numbers because this is the series for e to the x. And x equals 1, so we can plug in any x value we want, and we know that it will converge to some value, right? Yeah, this is e to the x at x equals 1. So this is effectively the series that approximates the value of Euler's constant, the value of e. So we know this converges. So I'm going to write that up here. So suppose I wanted then to look at this series. So here's my new series. It is 7 plus pi squared minus 4 plus 1,000 plus 1/3 plus 1/7 plus 1/25 plus, and so on, following the rest of it, following this same pattern. Which, what is this pattern? Right. This series, I'm going to write it down here. This series is the series 7 plus pi squared minus 4 plus 1,000 plus the sum from n equals, we'll just say from n equals 2 to infinity of 1 over n factorial plus 1. Yeah? You all agree with that? What can you tell me about this series? Does this series converge or does this series diverge? Exactly. This series should converge. And the reason why it should converge is by direct comparison to the sum from n equals 0 to infinity of 1 over n factorial, which we know converges. Right? So there is some point within here where, and it happens to be right here, where every term after this one and every term after this one, right, after 1,000 and after 1, in this series, every term is greater than every term in this series, right? Third is less than half. 7th is less than a 6th. The 25th is less than a 24th. And so since these ones are always bigger and this one converges, this one with terms that are always smaller must also converge. It doesn't matter what happened before it, because everything before it is just some series of terms, right? Which can be added together to form some number, and some number plus some other number is just going to be some number. It doesn't tell us what this series converges to. It just tells us that the series converges. Does that make sense to everybody? Okay. What if I gave you the sum from n equals 2 to infinity of 1 over n minus 1? What does that series look like? What's the first term of it? 1 over 2 minus 1, or just 1, right? Minus what? Or sorry, plus what? 1/2 plus 1/3 plus 1/4, and so on, right? What could we say about this series? We should be able to say that this one diverges, right? We would say that this diverges by direct comparison to what series? Yep. by direct comparison to the sum from, doesn't matter where we start, n equals 1 to infinity of 1 over n, which is, well, this exact same series. And we would say which diverges. And you could either say by p-series test, or you could just say it diverges because it's the harmonic series. And either of those would be an acceptable reason for why that series diverges. Right. And so if I look anywhere in here, every term in here is greater than or equal to the next term, right? The one that the next term in the other one, right? 1 is greater than or equal to 1. Half is greater than or equal to a half. A third is greater than or equal to a third. These are the same series, right? Just depending on where I started my summation. So by direct comparison with this other one that we know converges, I'm saying diverges, we know that this one will also diverge. Everybody good there? That's the basic idea of how this direct comparison test works. So now we're going to apply it to something a little bit more complicated. We're going to try to prove that the sum from n equals 0 to infinity of x to the 2n over n factorial squared converges for all real values of x. So first off, let's look at, is this a p-series test problem? Can we use the p-series on this? No, definitely not a p-series. Second thing we should look at then is the nth term test for divergence, because if I can just look at the nth term and show that it's not 0, I can immediately say that this diverges. So if we look at the nth term test, we'd be looking at the limit as n approaches infinity of x to the 2n over n factorial squared, and which one of those is growing more quickly than the other, x to the 2n or the n factorial squared? Is this going to infinity because the numerator is growing faster, or 0 because the denominator, right? The factorial grows faster, so this is going towards 0, which tells us that it isn't guaranteed to diverge, but that it could still diverge potentially. So now, what does this series remind you of that we might be able to compare it to? A series that, in fact, we know does converge for all real x. Right. So let's compare it to the sum from n equals 0 to infinity of x to the n over n factorial. Right? Very similar to the one that we've got, right? So how will we go about doing this? And we know that equals e to the x, right? Which we know converges for all real x. Any thoughts? What should we do? Let's write out the terms. How about that? Or actually, is there a way to rewrite x to the 2n over n factorial squared? X to the 2n could be written as x to the second to the n over n factorial squared. And so let's write these two series side by side and see what they look like. So this one looks like 1, when we plug in 0, it's 1, plus x squared plus Next one should be x to the 4th over 2 factorial, which is 2 squared, so over 4. And the next one should be x to the 6th over 3 factorial, which would be 6 squared, which would be 36. Right? And then what if we write out the other one? What does this one look like? This one should be 1 plus what? Should be x, right? Plus x squared over 2 plus x to the 3rd over 6. Is there a way that we can look at this one that we can line these up so that we know that one of our terms is always greater than or equal to or less than or equal to the other one? Like the terms from the other series? So no, Nick, it wouldn't just be the terms after 1 because we have an issue here. That depending on what x is, sometimes these terms are going to be bigger and sometimes these terms are going to be smaller. So yeah, we can't do every other term. We have to do every term. So we've got a small issue here. Maybe this series isn't the one we need to compare it to, right? So let's see. Somebody told us to compare it to x to the n over n factorial, right? Which seems reasonable because it looks very similar. But that creates a little bit of a problem. How could we manipulate this into a series that we would still know converges for all real x, but is even closer to this series, x to the 2n over n factorial squared? Yeah, good. Right. We'll make it x to the 2n. And if I just make that an x to the 2n, what's going to happen here? This will become e to the x squared, but e to the x squared should still converge for all real x, right? Because all we're doing is replacing the x with an x squared. And so the interval of convergence for x to the n over n factorial is all real number as well. Putting in an x squared, to solve for that domain, taking the square root is still going to be all real numbers, negative infinity to infinity. And so what does that do to us? This squares each of these terms. And if it squares each of those terms, now what are we looking at? We're looking at 1 plus x squared. That's the same as this one, right? Plus x to the 4th over 2, x to the 6th over 6. And each of these powers is now going to be the same. And we should be able to see that this series, for n greater than or equal to 0, each term in the sum from n equals 0, I should put it up here so you can actually see it. Each term in the sum from n equals 0 to infinity of x squared to the n over n factorial squared is less than or equal to this term, the terms in x squared to the n over n factorial. Would you all agree with that? And so we would say by direct comparison with this series, which converges for all real x, this series also converges for all real x. Good or no? Any questions on that? So what you'll need to do when you're doing direct comparison problems is you're going to have to find a series with which to compare your series to that you either know converges and that you can find your series is always less than or equal to that series, or compare it to a series that you know diverges and your series is always greater than or equal to that series that diverges. And you'll want to use generally for right now P series as your comparison functions, or regular old power series that we're fairly used to by now. Any questions on that so far? All right, hopefully we can get through a little bit more here. We got just a bit more I want to talk about. So all these tests that we've been doing so far, right? The integral test, and the P series test, or just the integral test and P series, or the direct comparison test, we had this little caveat at the beginning of them that said, as long as these series are always positive, right? Well, not all series are always positive. So we need a way to show what happens with a series. It's not necessarily all positive. So what we're going to do is we are going to prove that if a series does what we call converging absolutely, as in the series of a sub n, whether it's all positive or sometimes positive and sometimes negative, or always in negative terms, if the absolute value of that series converges, we call that converging absolutely. And we want to prove that if a series converges absolutely, then the series actually just converges. And this is true. Absolute convergence implies convergence. And so we're going to try to prove that right now. It should just take a second here. So we're taking some random series of, a sub n's, right? I'm just going to put a sub n. I didn't put the summations in here, but remember that this is a series of a bunch of a sub n's. Right? So the series that I have, right, any series that you have should always be less than or equal to the absolute value of that same series. Because if my series is always positive, then my series should be equal to the absolute value of that series. But if some of the terms in my series are negative, then my series will be less than the absolute value of that series. You all agree with this half of the inequality? Okay. This half of the inequality should make about the same amount of sense, right? If my series is always positive and I take the absolute value of my series, well, then they should be the same. But if I make this negative, this is definitely less than my original series. Or if I have some of my terms are positive and some of my terms are negative, if I make them all positive, but then make them all negative, this series should again be less than the original series. Or if all of my terms in here are negative, then I make them all positive by taking the absolute value. Then I make them all negative again by putting a negative in front of it. These two series should be exactly equal to each other. Y'all agree with the left-hand part of that inequality? I hope. Okay, perfect. So what we're going to do is, because we have some ways to determine whether the absolute value of a series, whether a series with all positive terms converges, we are going to say, assuming the absolute value of the sums of our series converge, So assuming this converges, okay, and given this inequality that must be true, we should be able to prove that just A sub n also converges. But keep in mind, this only works if the absolute value converges. So if we have absolute convergence of a series, we should be able to prove that the series itself converges. And the simple way we're going to do that is we're just going to manipulate this a little bit. I'm just going to add the absolute value of A sub n to each of these. I guess I don't need to put the inequality in there. I'm just going to write this. And what does that give us? If I add the absolute value of A sub n to each of these three pieces, which is a perfectly acceptable thing to do to an inequality, right? What does the first one give us? If I have the opposite of the absolute value of A sub n and I add the absolute value of A sub n, what should this one be? Should be a 0, right? Good. So 0 ought to be less than or equal to, well, this one just becomes absolute value A sub n plus A sub n. And this one becomes 2 absolute value A sub n. Everybody agree with that? What can you tell me about this? Does this converge or does this diverge? It should converge, exactly, Darius, right? The absolute value of A sub n converges. If the absolute value of A sub n is just some number, 2 times that number is just some number, right? So this converges. And what can you tell me about these terms right here? They should be all positive, right? Just based on the fact that this is always greater than or equal to 0. And so since this is always positive and this is always less than or equal to this is also all positive, which we should be able to tell because it's got an absolute value and we didn't multiply it by a negative. And if I have one series that has all positive terms, which is always less than or equal to another series that has all positive terms, this should converge by what? By direct comparison, right? Okay, so we now have at least proven that the absolute value of A sub n plus A sub n converges. Yes, no, maybe? Everybody good with that? We use direct comparison with the series of 2 absolute value of A sub n. This one, we had all positive terms here. We had all positive terms here. We knew that this one converged, and we knew that this one was always less than or equal to this one. So by direct comparison with 2 absolute value A sub n, absolute value A sub n plus A sub n must converge. Everyone's good there? Okay. So now we're sitting here looking at this. We have absolute value of A sub n plus A sub n converges. And we also know that absolute value of A sub n converges, right? So if I have absolute value of A sub n plus A sub n, which I'm going to write converges, minus the absolute value of A sub n. So if I take this other series, what do you know about this one? This one also converges, right? So this is just some number, and this is just some number. So if I have some number, and I subtract some other number from it, what should I get? I should get some number. And if it just equals some number, that means that it converges. And so we can say that absolute convergence implies convergence. So if I can prove that the absolute value of a series converges, that guarantees me that the series itself converges, which is going to allow us to get around this problem of we need each of our series to have all positive terms for all these tests we've worked with so far. And pretty much every test we're going to work with, the rules say you have to have positive terms for those tests to work. But if they don't have positive terms, we just take the absolute value of them, do it with those series, and then from there, since if that converges, we can then say that the original series converges. Does that make sense? Hopefully so. All right, so last problem. We got 5 or 6 minutes here. We should be able to show that the sum from n equals 0 to infinity of sine of x to the n over n factorial will converge for all real x. So the first thing that we want to think about is the nth term test for divergence. I'm not even going to write it down this time. As n goes towards infinity, this number in the numerator is always between -1 and 1 over some giant number down here, right? It's going to go towards 0. And so the nth term test for divergence doesn't tell us anything. What can you tell me about the terms of this series in terms of being positive or negative? Are they always positive, or are some of the terms of this series for some values of x negative? So let's say, for example, I plug in 3 pi over 2. No, that's not a good, yeah, that's a good number to put in. Suppose I put in x equals 3 pi over 2. This sine of 3 pi over 2 is -1, right? And anytime I have an odd power up here, what sort of term am I going to get? I'm going to get -1 to an odd power, which will stay as a negative number. So we're going to say our terms are not all positive. And so we can't just use any of our tests with this series. We will have to look at the sum from n equals 0 to infinity of the absolute value of sine of x to the n over n factorial. And this definitely has all positive terms. Do you agree?
Yes.
Now tell me about sine of x to the n. Always between what two values? Always between -1 and 1. Good. And so what about the absolute value of sine x to the n? Should always be greater than or equal to 0, less than or equal to 1. Sorry, I should have not put that n is supposed to be inside of those absolute value there. Do you all agree with that? If I take the absolute value of sine of x to the n, that should always be between 0 and 1, inclusive of 0 and 1. Okay. So what series do you think we might, knowing this, be able to compare this series to? That will always be greater than or equal to this series. It's going to need to have an n factorial still in the denominator probably. But what number could I put up here in the numerator? Couldn't I just put a 1 there? Wouldn't this always be greater than or equal to this? Like the n factorial doesn't change, but sine x to the n is always between 0 and 1, and 1 is always 1. And so if I compare these two together, the sine x to the n one is always less than or equal to 1, and the n factorial stays the same. So the numerator is always less than or equal to 1, which makes this series always less than or equal to this series. Everybody agree with that?
Yes.
Okay. And so what do we know about the sum from n equals 0 to infinity of 1 over n factorial? Well, this, I'll make a little side note over here. This is just the sum from n equals 0 to infinity of x to the n over n factorial with x equal to 1. And we know that this series here converges for all real x, including at x equals 1. So we know that this series converges. So by direct comparison, this also converges. Everybody agree with that? And we'll say for all real x. That says including at. I assume you meant what is the word after all real x, Nick, right? If this is including at x equals 1. Yeah. And so we could say that this, by direct comparison, converges for all real x. Everybody good there? Is this good enough to be done now? The answer is no. And since absolute convergence implies convergence, we can now make that same statement. The sum from n equals 0 to infinity of just sine x to the n over n factorial without the absolute values on it also converges for all real x. Good or no?